How many people here know what a Markov algorithm is? That's more than I expected. That's great. Okay, so you probably never heard of a cellular Markov algorithm. There's a reason for that. Most people know me as a puzzle guy, which is the left side here, but I'm really more of a software guy. And so this is more software-ish. So Markov algorithms date from 1951, not the Andrey Markov you all know, but his son. So they're not related to Markov chains or models. They are deterministic. They're Turing complete. We should really be saying things are Markov complete instead of Turing complete, but Turing beat him by 15 years. They're completely equivalent to Turing machines. We can map back and forth. But Markov algorithms are different. They're stateless. They operate on an entire string at once. They have an ordered set of rules. So I built a Markov processor. This is actually the second time I built a Markov processor. And I added something called a macro, which lets you condense a Markov algorithm significantly, which I'll show you in a minute. So the rules in a Markov algorithm, unlike a Turing machine, show you what will happen. I'm going to show you some rules in a second. That makes them much easier to understand and a lot less folding of paper than the Rule 110 example we saw earlier. So they're a little more better on your fingers. So here's a couple sample rules. And these actually illustrate some macros. So the first rule says take any character and add the token scan before that character. So, if you were doing ASCII, there would be 127 rules, but instead it's just one rule. Second one says take the scan token followed by any lowercase letter, change that to be the uppercase letter, and get rid of the scan token, add a skip token. So that would be 26 rules, but it's only one rule in here. So here is a Markov algorithm which will make something into headline caps. And I'm going to show you that running. And voila, that ran it, and we can now see that the Markov algorithm made the sentence. And if we were to write a Turing machine for that, how big would that be? I don't really know. So that rule is, I don't have the number here, but obviously it's only 9 rules, and it would be hundreds of rules if we didn't have the macros. So here is some additional sample rules. So take the start token followed by a vowel. Take the vowel, remove the start token, add a Y token at the end. Second one takes any 2 letters with a drag token in between, swaps the 2 letters, so 2 then 1, and puts the drag token at the end. Anyone know what's coming next? Pig Latin. Pig Latin is 28 rules, or it would be 7,000, whatever that number is up there, 7,238, I think it says, if we didn't have macros. So letter would be 676 rules, or it's 1 rule with a macro with 2 letters. So there's the whole Pig Latin, and you can see Pig Latin running. And notice it's even getting the capital letters correct. Because, you got to be a perfectionist. No one said this was fast. It is faster than folding paper, but other than that. So I learned about Pig Latin. Not Pig Latin. I learned about Pig Latin when I was a kid. I learned about Markov algorithms, when I was in high school, and I always found them fascinating. And the fact that you could write rules that were sort of readable and the thing made sense was cool. And I thought we can do better than this, and so I invented this idea of a cellular Markov algorithm, which is 2-dimensional. And they're very, very similar, but they operate on an array of cells instead of a string. And they are, of course, equivalent because they're both Turing complete. It can be much harder to map a cellular Markov algorithm back to a regular one. But going the other way is easy. Because we can operate on cells, it can be an order of magnitude smaller than a regular Markov algorithm. So the hard part in coming up with this was to have a representation that really worked. So the rules show visually what's going to happen, And specifically for 2D data, they are way easier to understand. So here's a sample rule. Take any region of cells with an up, left, right, down, and put an X in the middle. So there's two extra things here. The dot says any cell, and the dash dash says don't change that. And it's important that any changes like that don't affect the computational power. There's no extra thing added here. It's just a shortcut. So we could do this with a standard syntax, but dash dash is much easier than say, just leave it alone. So here, what can we do? Well, obviously cellular automatons. We can solve grid puzzles. We can do Conway's game of life. So here is part of Conway's game of life. And of course, there's the 4 fundamental rules of life. And those are written here as these rules on 3x3 grids with macros. So the first one is the underpopulation. And it recognizes that case and changes the middle cell to be next is going to be dead, next state. And then the second one is the survival rule. All 4 rules are like this. And there are 5 additional rules because to do something like this, you have to mark and sweep so you don't get the generations confused. So here it is. Super fast. And so I'm going to flesh this out more. I might write a Sudoku solver, which would be kind of cool. Does anyone here have a Erdős number wants to collaborate on a paper? And I wrote this in Python, but I am thinking of making a JavaScript version and releasing it online. And that is that, and then one extra thing. This is my gift, which is completely unrelated. But a note is that 3 of the bags might have a 7th piece. And if you have a 7th piece, just toss it, because it will make it very hard to solve this puzzle with an extra piece. Anyway, that's it. Thanks. Happy to, if you want to grab me later and ask questions or anything, I'm happy to chat about this.